So this is lecture 12, and what we have looked at previously is dimensionality reduction algorithms, and today we're going to look at a completely different topic in machine learning. So just to recap, if you guys remember previously, all the problems that we tried to solve are related to supervised learning, right? So whether we did, we used classification or regression, what we had first, we had a feature space. So in this feature space, we store all our samples, okay? Each sample is represented by D features, okay? And then our goal was to map or learn how to predict a target label or a target score from these features, right? So this is basically supervised learning, because first in the training stage, we use both the feature space and the label space, and we try to connect them through this mapping or through the parameters that we're learning. And if we have a testing sample, then we give our model the new sample features, right? And then we will predict the label or the score. So if it's like classification, it's a label. If it's a regression, for example, it might be a score, okay? So what are the issues related to this one? So here is a question. So what if the data we have, the training data we have, is not labeled? Now look at this example. So these samples, they have features. We know that they should belong to different groups, okay? But they are not labeled. We know that labeling is very time consuming, especially, for example, for high dimensional data. Like if you're using medical data or medical scans, it takes a lot of time to label those samples. So ideally, in an ideal world, we will just, rely on the feature space, okay, and somehow be able to predict the label without using the label space, okay? So this is the goal. So here, what we want to do, we want to learn how to group those samples, how to label them without using any labels in the training step. And here, let's look at this example. So what do we have? We have different samples, and this is the feature dimension and the sample dimension. So we have like 8 samples, and our goal is to basically classify those. So if we put them all together just randomly by order, so I concatenate all those samples in a matrix one by one, okay? And what do you guys notice? So if we look at this matrix, we don't see any particular pattern appearing in the data, where it's just a simple concatenation of a bunch of samples. But if we take this, if we, for example, do it this way, right? So you will start seeing that we are somehow uncovering a pattern in the data. So there is something hidden that we couldn't see when looking at the scrambled samples, but now that we know how to order them, we can see that they cluster in 2 different groups, okay? So what I have done so far right here manually is called unsupervised learning, right? So our goal is to discover hidden patterns about the data, or to learn how to group different samples in different groups or clusters. For example, using unsupervised learning. Unsupervised learning has many applications. We can use it for feature selection. We can use it for clustering, for grouping samples. But today we're going to focus particularly on the problem of clustering. So you might think that this is quite easy, right? Like it's, like you just compare samples and you will be able to tease them apart. But if we increase the dimensionality of the data, what do you guys notice? It becomes even more difficult. Can you cluster these guys? Can you group them in different groups automatically? No, it's very difficult, right? So this is why clustering is one of the hardest problems in machine learning. And there are different approaches. So today we're going to look at two. And these two are a bit like slightly different. So the first one is we will just look at the concept of K-means clustering algorithm and hierarchical clustering algorithm, which is a bottom-up clustering algorithm. So let's start with K-means. So here I'm going to just explain the key concept, and then we'll look at the algorithm. So who knows how K-means works? Okay, a few of you. Okay, so let's revise together. So first thing, given a data set, so this is our raw data. And what we want to do, we want to cluster the data into two groups. So to do that, we define two centroids, or what we call them, centers for the clusters. So this is, the centroid for cluster 1. For cluster 1. And we have another centroid for cluster 2. Okay? So next, once we randomly pick those centroids, so we pick two random samples, what we do, it's very simple. So the algorithms goes this way. We compute the distance between all other samples. So each point right here, let's take this point. We compute its distance to the centroids, so centroid 1 and centroid 2. So if it is closer to the first centroid, then we assign it the same label. So we label basically all remaining samples by proximity to centroids, okay? So in this case, this point will be colored in green, so because it's closer to the green centroid. Now for the other guys, you guys can intuitively see that all of those are closer to the yellow one than the green one. Okay, so then the remaining points, all of them, we will label them in yellow as belonging to what? Cluster 2. Right. Now this is step 1. The next step is interesting. So what we need to do is update the centroids. So this is just an initialization step where we're just, picking randomly 2 points of the data. Then once we assign all points a particular label or cluster, then we need to update the centroid. How to do that? There are different ways, but the easiest way is to take the mean. So we take all points belonging to the first, to each cluster, let's say cluster 2 here, and we average them. Okay, so we average all the positions and we get a new centroid. So if we average all those points, maybe the average position will be right here, somewhere right there. Okay, now for the second one, also we do the same. So this is the new centroid. It's the average of these two guys, right? So these are the two new centroids, and then we repeat again. So what's the next step? We label remaining points based on proximity to centroids. So here we have these points are closer to the green one, so they're labeled in green, and then the other points are closer to the yellow centroid, so I label them this way, right? Now you guys can see we're almost there, right? So we're teasing apart these two groups. Now the last step would be to update the centroid. So right here we compute the average across all these points. So maybe it locates around there, and then this is the updated centroid, the last ones, and we color our points. Next, what we want to do is again update the centroid. So if we want to update them, what do you guys notice? They stay the same. So they are stable, right? So because they are stable, this is the convergence criterion of K-means. So now you guys know how to run it. Let's look at the algorithm. So the algorithm goes this way. So first, we have our inputs. So the data samples, we have n samples. First thing, we need to specify the number of target clusters. So you need to say that I want to cluster my data into 2 clusters or 3 clusters or 4. So K is a parameter to preset in K-means, okay? So then we will repeat until convergence. For each point xi, find the nearest centroid. Cj, right? And then how do we find that? So it's just, the minimum distance. We compute the minimum distance between sample xi and all j's, all centroids, and pick the centroid that is closest and label it that way. So assign the point xi to cluster j. And then the next step is for each cluster, we need to update the centroids by, each centroid in cluster j gets updated by averaging all points xi assigned to the cluster j in the previous step. Okay, so it's pretty straightforward. And then the stopping condition would be when there's no change in cluster assignment. So everything stabilizes, right? Okay, so let's look at a three-dimensional case. So we're going to run it again step by step. So here what we have, well, two centroids, centroid of cluster 1 cluster 1. So the first thing we need to do is compute the distance between the centroid and all other points. So you can see that these points are actually closer to the yellow centroid than the orange one. So all of those will be labeled the same. And for the other one, these guys will be labeled in orange. So now you guys see. So because these are the closest to the centroid, so in that case we will just label all of those guys in orange, and then you can see how k-means splits the space, right, into two different groups. Now what is the next step? Yes, so update the centroid, so calculate the means. So we need to update the centroid. So right here I was right, so let me just put it the right way. So we update the centroid, so maybe somewhere right there. And then for the second one, it's around there. Okay, so and then here we do the same thing. So we compute the distances. So we know that these guys are closest maybe to the yellow one, right? When compared to their distance to the orange. So all these guys will be labeled the same. Maybe this is an ambiguous point, but still we will assign it to this cluster, right? And then this one will be closer to that one, right? And then here we go. So now we can label all of them. So if I get it right, so all these guys will be labeled the same. Now you can see like slowly we're converging, right? And then the next step, which is the final, almost final step, we update the centroids again by averaging all orange points. So this is, the new center right here, and then the yellow ones. This is the new center right there. And we're going to repeat this until ultimately our goal is to get what? Is to label all of those. So these are the orange samples, and the other ones are basically the yellow samples. You guys get it, right? So it's very easy. Great. Now, the goal is, right, so here is the thing. This is the distance that we're minimizing. So k-means basically, it minimizes the distance, the average distance, between each point and the centroid assigned to that point. So let's say, for example, we take point xi, and what we're trying to minimize, so let me just... What we're trying to minimize is the average distance to each centroid. So we compute the average distance to centroid 1 and average distance from samples belonging to this cluster to centroid 2, and then the third centroid in this case. And what we want to do, we want to find, to minimize this overall distance. Okay, so this means that our algorithm works well. Now, k-means have several issues. So let's look at this. What do you guys know this? So these are different initializations of the centroids, right? So k-means can be easily perturbed, or the results, the final results, the final clustering groups might vary a lot depending on how we initialize it. Because remember, the first step is to randomly pick 2 points from the whole data and consider them as centroids. Okay? Now, if we, and you can see like in these 3 cases, the first one with this initialization, we have a very good clustering. The second one, we had a mix between basically this small cluster was split into 2. These 2 clusters were merged into 1. This is not good, right? And also for this one, the third case is not a good like initialization. So how can we potentially solve this problem? Any ideas, guys? How can we solve this problem? I'll give you a minute to think. By what?
By using the infinity propagation instead of Kmeans.
Good one. Using affinity propagation. Right, yeah, that's actually one of the strengths of affinity propagation as a clustering algorithm. But let's say we want to stick with K-means and still work it out. What can we possibly do? So remember, we have all our points. So for example, these are our clusters. Okay?
Maybe multiple initializations?
Multiple initializations, yes. So that's a good idea. So basically what we can do is randomly pick different centroids. So maybe, so this is for cluster 1, cluster 2, and cluster 3, and repeat again. So we will run this many times. So this is the first initialization. Maybe second will be something like this. Okay, it's not really good. So we will pick maybe the same points that belong to the same cluster. So we're going to repeat it many, many, many times, like thousands of times. Like, yes, sometimes you need like thousands of initializations. But how do we know which K-means is the best, which results are the best? So let's say, for example, I run K-means 1,000 times, okay, with different random initializations or selection of K centroids. How do I know which K-means is the best out of those 1,000? Take the most
repeated outcome.
The most repeated outcome. So basically, right, so if you see an overlap between clusters across those 1,000 runs, so you will basically believe that this is a good clustering, this is a good results for the clustering. That's a good intuition, but there is something more robust. What can we do? So if you guys remember, what are we minimizing? Let's look. We're minimizing this distance, right? So we're gonna run K-means, and then ultimately we can select basically the results that achieve the minimum distance, right? Very intuitive. Because this distance, let's say for example, these are, let me do a diagram. So these are my K, my n,000 runs, and this is the distance. Okay? So maybe it fluctuates a lot, so we'll see something like that across 3 runs. So if we look at this graph, we know that this is the best result. Okay? Great. Now this is one very simple way of handling this. Now another problem, how to fix the K. How can we know, for example, because remember, all you have when you look at your data, let's go back to the first slide. So when you look at your data, all you have is this matrix. It's actually this matrix. You don't even know how many groups there are, how many, like, you know, in the data. So how can we find out if, well, we need to select 2 groups or 3 or 4? How can we automatically fix the K for K-means? Repeat for multiple K, yes, and then? And choose the one that minimizes the distance. Yes, that's it. So we need to repeat for multiple k's. And then at some point, we will see that we'll get a curve that looks something like this one, the green curve. And then starting from a particular value, specific value of k, that's called k star, the performance is quite stable. So we can select this value basically. Okay, great. Now, I have a very interesting question. What if the samples lie on a non-Euclidean space? So, what is a non-Euclidean space? Some of you might know, others might not. Who knows what a non-Euclidean space is? Somehow, okay. So basically, intuitively, in a very simple way, or put simply, let's say in a three-dimensional space, you have your points, or in two-dimensional space. If you want to compute the distance between your points, you just take the coordinates, right? So you have your x-axis, your y-axis, right? And the distance between 2 points is very intuitive. What do we usually use? We simply use the Euclidean distance, which is what? A straight line, right? Between these 2 points. Now, if we are in a non-Euclidean space, it's a curved, you can think about it or imagine it as a curved space. We can call it also a manifold, like something like this. Okay, maybe something like that, right? So it's a curved space, it's a high dimensional space, but if we want to go from this point, we want to average these 2 points. So remember, k-means updates the centroids by taking the average of the points belonging to the cluster of that centroid, right? So generally, we use Euclidean distance. Now, if we are in this space, and you can think about it as, you know, we have 2 mountains here, right? And you want to go from mountain 1 to mountain 2. So the shortest distance, the distance between them, the Euclidean distance is this one, right? So that's the Euclidean distance, the straight line that joins these 2 points, if you think in an Euclidean way. But actually, the distance between these 2 points is the shortest path. So you need to walk downhill and walk uphill along this non-Euclidean manifold or high dimensional space to reach that point, right? So this is the real distance. So this is the distance that we call also the geodesic distance, that, or the shortest path that connects 2 points on a non-Euclidean space. Now the problem with k-means, if your data lies on a manifold and it's a generally high dimensional data, and in machine learning those high dimensional samples generally lie on a manifold that is curved, that's not, you know, sometimes not smooth. So this is a very strong assumption to make, that everything lies on a Euclidean space. Okay, so k-means cannot be applied to a non-Euclidean data because the mean right here, if you compute the centroid, it will locate right there, but it's not actually the right position. So to be able to apply k-means, you need to make sure that your data lies on a Euclidean space. So this is one of the things. Okay, otherwise, for example, the center, the Euclidean center of these guys is right there, but using if the 3 points lie on a non-Euclidean space, this point might be far away somewhere, I don't know, it won't be at the center, it's not the center of gravity. Okay, so this is not a good approximation of the centroid in that case. And there are variants of k-means that work on manifolds. There are like many variants of k-means. Okay,